So today we're learning all about reaction yields, and we're going to be learning how to calculate the percentage yield in any chemical reaction. So all these stoichiometric equations we've been learning about so far, all of that is to tell us the theoretical yield of a chemical reaction. So maybe you're given some reactants, how much product do you expect to get out of that? But real life is always worse than the theoretical, right? In real life, you never get quite as much product as you expected. And why is this? Well, there's actually a lot of different reasons. The first problem is that whenever you're doing a stoichiometric equation, you're dealing with the reaction that you expect to happen, the reaction that you're going for. But there could actually be some competing reactions. Some of those reactions might be stealing your reactants. So one example of that would be, let's say you're trying to react propane with oxygen gas in order to make carbon dioxide and water. So that would be complete combustion, right? That's what you get if you have lots of oxygen gas around. But it would be possible for maybe you not to have quite as much oxygen gas as you want, and so you might get an incomplete combustion reaction happening at the same time. And that reaction would be producing maybe carbon monoxide and water, or maybe carbon and carbon monoxide, and maybe a little bit of carbon dioxide, but not as much. There's all kinds of different ways that propane and oxygen can react, and they're not all the ones that you're going for, your complete combustion, which would make carbon dioxide and water. So those other competing reactions will be stealing some of your reactants. Another type of competing reaction can steal some products. So an example of that might be if you were trying to react phosphorus with chlorine gas to make phosphorus trichloride. Well, that phosphorus trichloride will actually want to go on and keep reacting with the chlorine gas that's still all around it in order to create phosphorus pentachloride. So you're going to lose some of your products there for another reaction. So that's going to reduce your overall actual yield. The next reason why you might see a lower than expected actual yield is actually just that the reaction might not be finished yet. So reaction rate tells you how fast the reaction is going to go. And there's different things that influence reaction rate. One is temperature. If you want to put your reaction in the freezer, it'll slow down. That's something you might have done with glow sticks, right? If you bring a glow stick, you're playing with it, it's fun. I have little kids, so we play with these things. And then you put it in the freezer for a little bit. It'll slow that reaction down. And so the next day, if you want to use your glow sticks again, you can take them out and keep that reaction going and they'll still work. So lower temperatures will slow down the reaction rate. That means that if you stop the reaction too early, if you didn't realize that this reaction was going slowly, your actual yield will be lower than theoretical. Another thing that can really slow down your reaction rate is lower surface area. So that comes if maybe you haven't ground up your reactants enough, so they're not interacting with each other enough. Maybe you're trying to make coffee, but you didn't grind your coffee beans very well. It's not going to dissolve as well. The same thing happens with any sort of reaction, right? So a lower surface area, which means things are maybe more chunky, not ground as finely, will mean that the reaction rate will go a lot slower. And so you might not get the full yield because your reaction was too slow. Another issue could just be impure or diluted reactants, the same sort of problem. There's other stuff in there, maybe instead of what you thought you had, maybe there's something else in there. And the last one could just be your lab techniques. So maybe some of your reactant actually got stuck to a stirring rod, and so now it's been taken out of the beaker. So that's going to obviously reduce your overall yield. So at the end of the day, we find some actual yield. That's the actual amount of our product that we formed. And using stoichiometry, we found a theoretical yield, which on the bottom, that's what you expected to get. The percentage yield is literally just divide those two things. You divide the actual yield, what did you really get in real life, by the theoretical yield, which is what stoichiometry told you should have gotten of your product. And then to make it a percentage, we just multiply by 100%. So the key difference here is that the actual yield is measured in the lab, and the theoretical yield is calculated with stoichiometry. So let's look at an example here. We're going to look at the fermentation of glucose. So glucose will break down into ethanol and carbon dioxide. And we've got the balanced chemical equation there. So 1 glucose breaks down into 2 ethanols and 2 carbon dioxide molecules. Let's say we've got 20 grams of glucose reacting. And out of 20 grams of glucose, we're actually only creating 1.4 grams of ethanol. What we want to find is the percentage yield. So there's two things we have to find, our actual yield and our theoretical yield. The actual yield is given to you in the problem. That's the 1.4 grams of ethanol that's actually produced. But the theoretical yield you've got to calculate. So we'll start with that because we've got to do some stoichiometry. There's kind of three main steps to stoichiometry if we've got our balanced equation already. The first is to take the mass you're given of glucose and switch it into moles. So the equation here is that moles is mass divided by molar mass. I'm going to make sure that I'm talking about the moles of glucose, and that equals the mass of glucose over the molar mass of glucose. So I'm just being careful I've got all the same compound here. The mass of glucose that I'm reacting is 20 grams, so that's what I'm starting with. The molar mass of glucose, we've done a lot of molar mass calculations, so I'm speeding this up a little bit here. It's going to be 6 times the molar mass of carbon plus 12 times the molar mass of hydrogen plus 6 times the molar mass of oxygen. That all adds up to 180.18 grams per mole. Divide those out and you'll get 0.111 moles. So now we're in mole land. Once you're in mole land, you can do your fun little fraction, that ratio to get the moles that you want of your product, which is ethanol. So in our ratio, we're going to put balanced equation stuff on the right and stuff in the experiment on the left. So in the experiment, the thing I want is moles of ethanol, that goes on top. The actual moles of glucose is on the bottom, that's the 0.111 moles that I just found. On the right, I've got the stuff in the balanced equation. So the coefficient in front of ethanol in the balanced equation and the coefficient in front of glucose in the balanced equation goes on the left. So in terms of actual numbers here, that's N, that's my moles of ethanol on top, divided by the moles of glucose, which is 0.111. And then that equals the coefficient in front of ethanol, I can see that's a 2 in my balanced equation, divided by the coefficient in front of glucose, which I see is a 1 in my balanced equation. So do a little rearranging here. I'm going to multiply both sides by 0.111. That moles on the bottom, that clears it off the bottom on the left, right, moves it over to the right side. The dividing by 1, of course, doesn't impact things at all, so I just dropped it. Multiply that out and I get 0.222 moles. So that's the number of moles I have of ethanol. I'm close. I need to convert that back into a mass. So the equation I use here is that mass is moles times molar mass, but now, gotta be careful which compound am I talking about? I'm talking about ethanol. So I'm gonna find the mass of ethanol, I use the moles of ethanol that I just found with my little ratio thing, and I have to make sure I multiply by the molar mass of ethanol. Molar mass of ethanol is gonna be twice the molar mass of carbon, 6 times the molar mass of hydrogen. Be careful there's 5 hydrogens and then 1 more, right? So 6 times the molar mass of hydrogen plus the molar mass of oxygen. So that gives me my moles is 0.222, that's the moles of ethanol. The molar mass of ethanol is 46.08. Multiply that out and I got 10.2 grams. So the final mass of ethanol that I would expect to get theoretically, so stoichiometry tells me the theoretical yield is 10.2 grams. That's what I'm hoping for out of this reaction. Next, we look at the actual, right? The actual here is only 1.4 grams. And I have to divide those to find the percentage yield. So I'm going to take, what did I actually get? I expected 10.2 grams, but I only got 1.4 grams of ethanol being produced. So I take the actual amount of ethanol, 1.4 grams, divide by the theoretical amount that I should have gotten it if everything had gone perfectly, which was 10.2 grams, and multiply by 100%. And that gives me a 13.7% yield. So pretty small, right? And this sometimes happens in reactions. Our reactions don't go perfectly the way we want, and so we can't ever get an 100% theoretical yield. Something will always go wrong. And here, quite a lot of that glucose is not turning into the ethanol the way that we wanted it to. And that is how you calculate percent yield.